Welcome to a lesson on the trouble with centers and classifying behavior of nonlinear systems of ordinary differential equations. The trouble with a center in a nonlinear system is that whether the trajectory goes towards or away from the critical point is governed by the sign of the real part of the eigenvalues of the Jacobian matrix, and the Jacobian matrix in a nonlinear system changes from point to point. Since this real part is zero at the critical point itself, it can have either sign nearby, meaning the trajectory could be pulled towards or away from the critical point. An example of such a problematic behavior is the system given by x prime equals y and y prime equals negative x plus y cubed. X prime and y prime are both zero only at the origin 0, 0, which is the only critical point. The Jacobian matrix for the given system is the 2 by 2 matrix with entries 0, 1, negative 1, 3y squared, where f of x comma y is equal to y, and g of x comma y is equal to negative x plus y cubed. At the critical point 0, 0, the Jacobian matrix has entries 0, 1, negative 1, 0, which notice is invertible, and the corresponding eigenvalues, shown here in blue, are 0 plus or minus I. Notice here the real part is equal to 0, and therefore the linearization has a center. Recall if the eigenvalues are complex with a positive real part, we have a spiral source, and the stability is unstable. If we have complex eigenvalues with a negative real part, we have a spiral sink, and the stability is asymptotically stable. If we consider the Jacobian matrix, and then use the quadratic formula to determine the eigenvalues at any point x comma y, we get lambda equals 3/2 y squared plus or minus I times the square root of the quantity 4 minus 9y to the fourth divided by 2. At any point where y doesn't equal 0, meaning most of the points near the origin, notice the eigenvalues have a positive real part, since y squared will never be negative. This positive real part pulls the trajectory away from the origin, which we should recognize from the table below. Again, if we have complex eigenvalues with a positive real part, the behavior is a spiral source, and the stability is unstable. A sample trajectory for an initial condition near the origin is shown in the graph on the right. So here we have an unstable critical point, a spiral source, at the origin for the given system, even if the linearization has a center. The moral of the example is that further analysis is needed when the linearization has a center. The analysis in general will be more complicated and is more likely to involve case-by-case consideration. Such a complication should not be too surprising. By now in your math career, you have seen many places where a simple test is inconclusive. For example, the second derivative test in Calc 1 to determine maxima and minima, and therefore requires careful and additional analysis of the situation. I hope you found this helpful.